Yeah.
You're putting on your shirt now.
Hey, get out of my screen.
Yeah, the space.
I can upload on mine. So, should we read our question aloud?
We should.
Yeah, I don't need to read the whole question. Yeah, so essentially the question is about lungs and their volume as a function of time. And the information we're giving is that at 2 seconds, there's a low of 0.6 liters in the lungs, and then at 5 seconds, there's a high of 2.8 liters in the lungs. So from there, we can find the sinusoidal axis because that's just the in between of those. So the sinusoidal axis is 1.7, and then that gives us our.
So the math is found right here.
Yeah.
What basically do is
I mean, 4 minutes.
take the average of these, divide it by 2, get 1.7, and
You know what you
then
can do?
put that as okay. Divide that by 2, get negative 0.85 as our.
Interesting.
Yeah. So since we have 0.85 as our amplitude, we know that it needs to be a negative 0.85 because the cosine function is starting with the lowest point, which is at 2 seconds, or I mean for our purpose, and so from that we know that we actually need to move it. The phase displacement is 2, so it's x minus 2.
X minus 2, moving it over to the right.
So the
Two
cosine,
spaces.
so the function starts right here.
And our next problem was finding the period of the equation, which we obviously out of 2 and 5 we found that to take one full breath, it was 3, and then continuing off that to multiply it again to get a full sort of wave, it was 6. And with that being 6, we said, okay, so put that into this equation here, which is the period times b, which this value is b, equals 2 pi. So what we did was we divided that by 6, and we got b as pi over 3. And then we put that into our final equation here.
Alright, and then we plotted the equation. Plotted the graph. And then now we're on to our question. So one was find the amount of air in Karen's lungs if she starts holding her breath 3.5 seconds into the timer.
This one's.
So basically, wording's a little weird, but it's just saying what is her lung capacity at 3.5 seconds.
Which is a simple just putting 3.5 into, if you were to do this algebraically, you put 3.5 into x, solve this entire thing, you get 1.7, or if you graph it here with about x equals 3.5, you'll see that it's about the axis.
Yeah, but you can also kind of tell that, from 2 to 5, that's how long it takes to get from the lowest point to the maximum point, or to complete 1/2 full rotation. And 3.5 is midway between 2 and 5, so, and you know that 1.7 is a sinusoidal axis, so you don't even really need to do any math there to find that out. So yeah, so it takes, so the answer is it takes 3.5 seconds. No, it takes, there's 1.7 liters of air in her lungs at 3.5 seconds. And then the second question is find the first time Karen has 2.3 liters of air in her lungs. So, Decker, you want to explain the math you did?
So the math I did here was essentially, it was algebra, in an algebraic way. So
negative cosine.
writing this out, we see that you subtract by 1.7, yada yada yada, divide, all that good stuff. You take the inverse cosine to find this specific value here of 0.6 over negative 0.85 to equal pi times x over 3 minus 2 pi over 3. We got that by distributing this value here into this part of the equation to get that cosine. We just took that out. Nextly, we added 2 pi over 3 multiplied by pi over 3 to get this long equation right here, and then input the values to get about 4.25 seconds.
Yeah.
Brilliant,
So,
Nolan.
luckily, because the answer is between 0 and pi. Decker's answer was right, but you know, like that method might not necessarily give you the first time that there's 2.3 liters of air in a lung. So you can also just plug in the equation, our sinusoidal equation, and then the equation y equals 2.3 into the graphic calculator, which gives you kind of like that. I don't know if you can see. And you basically just press second and calculate, and then you can find that the specific intersection point that you want, because you know, there's infinite intersection points. So yeah, that's how we got that second answer. And then here we just have those two lines plotted, so you can see the intersection.
Visual thing to understand like when this is happening in the flow of time.
All right, that's it.